The universe is a big place. And I will be stopped before coffee by my voice, by the way. And I apologize to the people I spoke to yesterday because you might catch my virus or something, whatever. The universe is a big place, and what I'm going to talk about mainly is the issue of data analysis over large ranges of scales and how important scaling is. And this comes from work that we've been doing in Groningen. I've got my thing, actually. I've got my one. Mine actually works. Oops. Yes, better. And I want to talk about things like this, which is the most iconic picture of the 20th century almost, done by Valérie de Lapparent when she was at Harvard, reconstructing data. And this involves no statistics. The question is, that we're trying to answer is, can we analyze this and create the real underlying picture? And underlying all this is my wish to do this by having machines using neural nets of some sort, not necessarily convolutional neural nets, which will do the job for us. And we can have a nice discussion with Lieu about doing blind testing with neural nets because they are totally unbiased. They'll come to a decision, you have no idea why. So we get these wonderful representations of the universe, reconstructions. The one on the left is from Florent Leclerc, which is one of the most pretty ones. And this one is a completely mathematical reconstruction by Job Velderbrug and Rien van der Weijhart. And these are basically different representations of data. The question is, are they representations which are just single scale, or are they really multi-scale? Are they showing us everything, or are we looking through some kind of blurring lens which picks out a particular scale? This structure, this is a list of, not exhaustive list of all the people, but I wanted to acknowledge other people who play this game. There's a whole list of them, and I think it was Noam Liebeskind and Rien van der Weijhart classified the methods that you have here, and I'm going to be talking mainly about Hessian methods and how to make them non-local. But there's topological methods, which I'll also mention, that may be mentioned as well in the next talk, and the pretty pictures you can make from phase-space dynamics and such. It's a big industry, and it's even bigger actually outside astronomy, because people who work on MRI scans and things like this try to get real data with no biases, otherwise they might misdiagnose people. The medical industry is full of this stuff. So the team is students and a few other people from the Kapteyn Institute, which is where I'm from. I borrow my time, that's the list. And I shall try and talk about most of their work here, because they all work on pretty much in these areas. There are basically 5 areas. Voids here. Rien van der Weijhart in some sense is Mr. Void. And so therefore a lot of work is done here on voids. He's the void man. Web structure, which is largely what I've been involved in, which is multi-scaled analysis mechanism. Vlasov flows, which is what the cold dark matter flow is on large scales. And these reconstruction mechanisms, which you heard Florent Leclerc's talk yesterday, the excellent talk. I was going to talk a bit about barcode, but I think that's unnecessary in the light of his wonderful talk yesterday. Right, voids. The first paper on voids was a Dutch paper written by a Dutch scientist, Descartes, and he constructed this model of the universe. He wrote it while he was in Holland. He published it in Holland. He's Dutch. It's dated 1644, but he actually did it before that. So this is what voids are about, basically. And they occupy 77% of the volume of the universe. So they're important, but they only have 15% of the mass, but they're not empty, and I'll talk about that too. So, catalogs. Lieu and people love catalogs, because catalogs of anything and everything basically are good food for statisticians. And this catalog, 2 mass, has had the two-mass redshift survey, starting, I think, with John Huckrow, basically started really probing the universe in a wonderful way that with the Milky Way, let's go back a bit, okay. With the Milky Way sort of sitting across there, but very small interference in this case, unlike in the microwave background where the Milky Way is a pain. We've got the system here where locally there's a guy called Tony Farrell, who is now the late Tony Farrell, very sadly, very nice character. He actually sat down and identified voids in his own catalogues of galaxies and gave them names. And if you take the two-mass survey, as Johan Hidding did, and then reconstruct the universe within about 6,000 kilometers per second, you can see all the voids in his plotting of it here. You can just see that's the Milky Way going across the sky. Where's my laser beam gone? There you go. There it goes, across the sky. And you got all these voids, all these names were created by Farrell just simply by looking at photographic plates. So people did rather well with photographic plates before we had Bayesian analysis. It's the Bayesian brain which managed to do it. Okay. Now, one of the most powerful methods which we had and which was introduced about 10 years ago into astronomy in this paper here by Erwin Platt, oopsie daisy. Why do I keep pressing the wrong button? Here, Platten et al., 2007, is basically called the watershed void transformation. And this is an example of a very difficult multiscale problem because it's got gotchas all over the place. There are things that you don't know that bite you before you actually get to the answer you want, so you've got to start doing a lot of hard work to get there. This explains the process. You start off with a landscape in 2 dimensions. It's easy to visualize. It's the same in 3 dimensions. And you basically fill the landscape with water. Or you can go backward. You can actually drown the whole thing and drill holes in the valleys and have it all run out. But you fill it with water. So as the water level rises, some of the land here sinks under the water, and you get lakes in basins and things, so you flood the landscape. And eventually, you come to a point where most of it's under water, and you define the basins, the lakes, which are filled by the water level. This is good because this generalizes to n dimensions very easily, and the most important thing about this is that the first problem was solved by van der Weijhart and Schaap a long time ago, is how to resample a point set so that you can actually do this. So you've got to do this, you have to have the data on a continuous grid, so you have to take the data you've got and transform it, and the tool is called DTFE, the Delaunay Field Estimator, Delaunay Triangulation Field Estimator, which is a wonderful way, a mass-conserving way of resampling a set of points. And this underlies everything we do, is underlined by this one process. Now, there's a caveat emptor here at the end. Poisson noise are solved by you've got to do heavy edge preserving because there's Poisson noise in this. Your galaxy happens to be at one place, but it might have been somewhere else had the gravitational field been slightly different. So you've got to deal with that. And there's a whole pile. Why do I keep on pressing the wrong button? It must be. There's a whole pile of median filtering going on and smoothing, and the maps that we use are basically smoothed something like 12, 15, 20 times sometimes by using special nonlinear median filters just to get there. And eventually, you get some very nice results like this. We did this was done from a void comparison run several years ago by Kohlberg and co. And what you see are a selection of the attempts which were made. And the one we were involved in is that I've just rearranged the diagram so that we're in the middle. And this is Mark Nyrink's Zobov. He used, instead of using Delaunay field reconstruction, he used Voronoi directly to reconstruct the field. But you can see that these 2 reconstruction methods are done remarkably well. Now, so we know what a void is when we see one, but when you look into detail at this, I think, fairly successful attempt, the problem is there's structure within these voids. If you look here, this is an example of what scaling does for you. This is basically scaled, smoothed by 4 megaparsecs. These are the same maps smoothed on different scales. And these are the voids that are found. And what you notice is that, for example, despite the fact you've got a void here, there's structure in it still. So the void is not void. And the structures look like little voids, subvoids. So all the smoothing that was done to get this thing to work so effectively actually fell slightly short because we did not do it in a fully multiscale way. And it can be done. But then we come to the story of arbitrary parameters and such. It can be done provided we think of a parameter called void emptiness. The other one, the previous mechanism, which is simply to fill it with water, having smoothed the data lots and lots of times so there's no bumps and lumps inside the basins, which you're going to do. There's no little peaks sticking up. However, if you look at this, define this emptiness parameter here, which is the number of grid points in the void whose density contrast lie below a certain threshold. So instead of having -1 as the limit, because delta is the relative excess of density in this notation, so delta is 0 is the mean, and delta is -1 is emptiness. So you add an arbitrary threshold, and I'll come back to arbitrary thresholds in a short while. And the procedure is that you start with the largest scale, and you're going to go down through the scales, adding things to the story. So you mark all those, you only count voids which have more than an emptiness of greater than 50%. So they have to be properly empty voids, 50% empty voids, because then you'll find something inside them to keep on going down. This is a bit like baking a cake. It's a recipe. I'd like to find another way of doing it, and I think the answer will be neural nets of some sort, but that's a long story. And then you look at the next scale down, and you find all those empty voids, and so on you go. But there's a caveat again, that you don't register a void if more than 20% of its grid points will already belong to a larger void. So it's a very kind of arbitrary process, but it's a process that gets you down into the different scales. And this is an example of the process actually working. I did have a movie of it, but since the latest Windows update, I'm unable to show it. And so here, you start at the bigger scales, and you go down, and you add the yellow voids, and then you add, I don't know what color that is now because I'm colorblind. So you add different, I hate students who put multiple colors that I can't see. It's a real pain. And because I'm a dichromat, it's a bit difficult. So eventually you drill down and you get a map which looks like that. And the color key is on the left. And so the red ones are 4 megaparsec voids, 3 megaparsec ones are yellow, 2 are green, blue, and purple, grey, and cyan, I have no chance of seeing the difference between, so I'll allow those who have nice colour sight to have a go at it. The problem with this one, it's not really a problem, the result's pretty good, in fact, for our purposes. I mean, why would you want to know something's a void? We'll come to that. But the real problem is that we've got these numbers, 50 and 20%. So recently, Miguel Aragon, who'd been a student at Groningen and has been working on this project, this kind of stuff for 10 years, he just posted a paper on Archive, and it's going to monthly notices, I gather, in which he decides to build a huge convolutional neural net, stuff all the data into the neural net, train it somehow, and this is the question, and out pops the answer. I'll let you read the paper. I haven't studied it in detail yet, so I'm not going to comment on it. But I think the philosophy is good. And even though we won't understand why the network did what it did, it'll do it to the extent that we don't understand why our brain does what it does. So there's no difference. Also, one might well argue that people who do Bayesian analysis has become so complicated now that there's only half a dozen people who know about each technique. So if something disastrous were to happen to those half dozen, we'd never know how they got their result or what it was, because we're not going to understand or be able to reproduce their work. Neural nets have become really a panacea in the sense that, you don't know how it works, but hey, the results are good. And you can also get a job in Google if you work on that, which is actually rather good too. They pay rather well. So that's looking at a snapshot. And again, neural nets. Google's very good at looking at snapshots, but they're not very good at looking at videos. Here we have the universe is dynamic. And so redshift 1.5, the voids look like that, 0.43 and 0. And again, I have terrible trouble with these colors, because to me, they're not colors. The voids get bigger and more empty with time, and they get swallowed up and merge. And the color represents the percentage of voids in the volume with less than -0.8. So how do you define a void hierarchy? It's clearly hierarchical. It's doing a good job. So this mechanism works. It's a good mechanism. When things work, I think we should celebrate it, because so many things don't work when I try them. Right. And this is an example of the build-up of a void from the work of Matthias Dries. And so what you do, you start with a void at z equals 0 and trace it back in time, and all the particles in the and look, each particle traverses the voids that were merged into the final structure. So you say, right, I'm sitting in this huge void. What was I doing a short while ago? I was sitting in another void, and if it satisfies the 20% and 50% criteria, those horrible magic numbers, then you keep on going to keep on finding all the voids and sub-voids within that. And this is an example of the merger tree of voids. I think this is actually a rather good way of looking at halo mergers as well, in some sense. In fact, it's done in some of the cases. And so you can see the void. I've got a movie of this, but until about a week ago, it stopped. It was working, and then it stopped after some stupid upgrade. And so you see that they're all going into this one massive void you've got here, but they all started off as individual voids at different times. They suddenly appeared and became important. This is the movie. Does it work? Oh, yes, it's working. Look at that. Hey. And there must have been another update last night. So on the right, you're seeing a chunk of the universe model. This is two-dimensional. Oh, I've gone and destroyed it. No. Okay. So you're seeing this chunk of the universe blown up, and here you'll see the building of the tree as it comes up. And if you can watch two things at once, one eyeball on each, you'll see how it goes. Here you've got two voids, and that's all going to happen. And you're going to see some mergers happening in a minute between these voids. There you go. And this is the one we saw last. Oh. And eventually it becomes, everything goes clunk into one massive void at the end, like that. There we go. And so this is just simply a merger tree, but it's a rather nice way of doing it. There's another way of doing it. So we can describe one void. Here we were sitting in a void, and we can trace our past history, which void we were in, and we can see that structure reflected. I'll show you some pictures of the local group and things like that in a few minutes. I want to point out something. This is a slightly confusing diagram, I apologize, from Adelsbrunner and Hara, I guess, who really started this game. And the question is how you characterize birth-death processes. Problem started by Einstein and Smoluchowski a long, long, long time ago. Einstein seems to have done everything. Every time you pick something up, you find that in 1900 and something or other, he did something that you were talking about. So just consider any arbitrary function and define the birth of a phenomenon when it hits its maximum and its death when it hits its next minimum. Here's another one being created, and then it dies down here. So we're going to plot the birth date and the death date in this way. So when this thing appears, its birth date is there. And its death date is along this line here. And so the two lines, birth date, death date, is set at that point there. So this point describes the birth time and the death time. Birth time is about 2 and a bit, and the death time is 6 and a bit, 6 and a big bit, probably. And so there's a point there. And this next one, a huge one, basically survives there. So what you can do in emerging hierarchies, whether it's voids or halos, is basically to look and see when they were born and when they died. And clearly those who are born at the same time as they die are pretty useless, and they will lie along this line here. But there are people who hang around a long time, and they're a long way from this line. And so you can encapsulate all the information about the birth and death cycles of merging objects in just one plot. So what you get, if you look at the voids with 2 power spectra, this has been done again from the Matthijs-Dries thesis, and I believe Matthijs used code from Pratish Pranav and Michael Kerber, so he didn't write the code, I'm sure. So this is the birth-death diagram when you have a rather large-scale dominated spectrum. And when you have an n equals +1 spectrum, this is the birth-death diagram. And this is the log of the number of points which are involved in this. So there's the very darkest areas of where all the points are, and the very faintest areas, you only have a small fraction of the points. So yes, it's like humans. So a lot of them die at an average age, as it were, but there's some people with remarkable longevity. And so these persistence diagrams, as they're called, are a good way of summarizing the total evolution of the system in one snapshot. And you can even take, this is a ratio of these two, for example, and you can compare directly then what has changed between the two. You can look at it, but you can do this. And so you've got to define some kind of function, intensity function, and divide the two pictures. I hate the statistics of divided quantities. They're very unstable, but that's the best way, that happens to be the best way of doing it. So persistence diagrams like this, you're going to see them in a few other places. And I'll come back to that in a few minutes. Right. Now, oh yes, KRIGING. There was a mention of it in Florent's talk yesterday, so I thought I'd show a map of the Sloan survey reconstructed by nonlinear KRIGING. And it looks good. You can see, oops, I keep on doing that, I must stop it. You can see the Valérie de Lapparent stickman here in the Great Wall. And these are all the voids which have been found by using the watershed thing. And these are the large, very large scale filaments that you can see floating around. The reconstruction, the voids were found by watershed void found, and the map was created by nonlinear KRIGING, which is actually a little bit like constrained random fields. And that link I won't go into, but there is a link. Now, on this, you can look at the catalogue of galaxies you start with, and you can find galaxies in voids. This is the astronomy bit. So having found the voids, what use are they? Well, you're going to now identify the environment. There are really dense environments like filaments, and there are super dense environments like clusters, and things like voids, which are nominally empty, but they're not in fact. So by doing this, people were able to find some void galaxies sitting in voids, and got some observing time to actually go and see this. The paper is by Krekel et al. From 2011. And so to look and see if the galaxies in these voids were actually any different, because we now had a set of voids that we could believe, these are real voids, because the watershed transform does a good job. And that's how they looked. So they looked like any other galaxies you might randomly get in the Sloan Sky Survey. And so they did all kinds of things. They did multicolor photometry and things to discover, are these guys really, really, really different? And in fact, they are different. None of the great, beautiful systems you see with spiral arms and everything, they have very small stellar disks. They have perturbed H1 disks, and they have companions around them and everything. They're really ill-formed galaxies. They haven't had the same environmental nurturing of halo merging as you might have had before. The sample was based on about 60 galaxies. out of a total sample of about 400. They only had the time to measure those, but I think carrying on with this would actually be a good idea. People do numerical simulations and try to reproduce this, and there's a nice numerical simulation which is appropriate for this, work done by Stephen Reeder and Simon Portuguese-Svart. More Dutch work. Hey, I'm biased towards the Dutch. And what they did was they did a very high numerical cosmogrid simulation, which has got billions of points and done on worldwide computers. It's a good one. And basically, they sit on one of these galaxies. Here you've got void galaxy D, which is that guy, which is a model. And whether they look like the ones I showed you before or not, it's a matter of opinion. I think they don't quite, they're not mature. But you can sit on this galaxy and look at the sky around you as the sky collapses on your head. So this is at a redshift of 3.7, and then 5.7, I can't read it. No, can't read it. My eyesight's gone. So anyway, the different redshifts, 0.5 and 0, and you can see the sky is dominated by a sheet here with filaments in the sheet, which are going to collapse. And you can see that this structure becomes these two filaments, and they become one filament, and then they just collapse, and you get a satellite galaxy. So what I like about this, it would be nice to have a movie showing the sky collapsing on your head. Filaments, like galaxies, have dynamics, and the dynamics and merging of filaments is also very important. There's also things called supervoids that were found by the technique. And there's another catalogue drawn up by Brent Tully. And from the catalogue, he identified supervoids called V3, in this case, because it's part of the sky, V11, a few others floating around, and the ones we knew about Bootes and Virgo. And the watershed transform will find all those with no trouble at all. These may be relic BAO voids, if you like, because they'll have roughly the right scale of 100 megapart between 80 and 160 H1 minus megaparsecs. So there was also another study, just the same thing, which is a nice one, by Granite et al. And Mark Nyrink was the co-author of that. And they've used his VOBOS method to identify voids, and they identified red galaxies and things like that. And the importance of this is that if you look through voids and things, there will be a dip in the temperature of the microwave background, and it's basically the integral of the gravitational potential along the line of sight, normalized by c squared. So you do this integral, and you get a delta t over t. And there are two contributions from places where the gravitational potential has one sign, filaments, and clusters, and then there's another contribution from the voids, which has the opposite sign. And so here you see two maps generated. This is from the integrated Sachs-Wolf effect map generated from the red galaxies, and this is the void map. And you can divide one by the other. You can use a cross correlation. And what they showed, what Granite and co showed in 2015, was that there was indeed a correlation, because when they sort of flipped one mass and map and redid the correlation, you get this line across here. So there seems to be a signal of a correlation in the sky between the contribution from the positive and negative mass fluctuations. So the integrated Sachs-Wolf effect is obviously a good thing, good target to do, but you've got to sort out what it is you're seeing and where you're seeing it from. But, you know, so voids is good news. They're interesting. Now, in my remaining minutes, I want to talk about filaments. Again, the multiscale thing. This is where most of our work has been done recently. And basically, these are based on calculating the Hessian of a continuous density field, and you do it basically that way. It's a second derivative of the field. It's a matrix. And if you've got two coordinates, so it's like a map, you have two variables you differentiate with respect to, and this has eigenvalues. And the first time I met this, actually, was in a paper from Los Alamos National Security, applied mathematics and plasma physics of a cow which has been tessellated. And to this day, I haven't found anybody who knows why they wanted to tessellate a cow in a place which makes nuclear weapons. Maybe they're stealth cows they're going to drive across the border towards the Russians now. I mean, it'll probably be revived, I don't know. But the point about this is that you see that you have minima in the cow's ear, and you have maxica at the cow's udders and things, local maxima and things, and you can describe it through a nice tessellation, nice triangulation. But Hessians are very local. So if you want to describe the whole cow, you're going to have to do it in a scale-independent way. These maxima and minima are very important and have been basically exploited by a number of people, especially here in France, Thierry Sousby and people like that. And what you see here is one there and one there. You see minima, oh sorry, maximum ones with the circles around them. So that one, minima, and between maxima is a saddle point, a pass, in my language, looking at maps and driving cars. And there are lines connecting the minimum of a basin here to another minimum via a pass, which is how you get out there without climbing the mountains, and two mountains find a ridge. These ridges and things are exactly what the watershed void transform actually calculates. You get this is just a map of it, and this skeleton thing is exactly the ridge lines and these lines here. So there's a link between the watershed void transformation, an intimate link, and the and topology. We'll come to that. Right, let's move on. So now you've got your Hessian. You're going to calculate its eigenvalues, and you're going to dream up some algorithm which tells you what the shape is based on the local eigenvalues. That's local shape, very local. And the decision we're going to make is that a thing is a blob if they're almost all equal and they're all negative. A line requires two of them to be more or less the same and very much greater than the third eigenvalue, etc. And so you see here an n-body simulation, and these are the blobs, these are the filaments defined by this, and these are the sheets. Now, this doesn't look like much, so you've got to start working, again, more cookery, to get to what you really want. So what you do is, you take your particle set, you smooth it, you resample it using DTFE or something like that on a grid, and then you basically smooth this like mad. So you start at the very top resolution, and you can use 12 or 13 layers of smoothing. In the way I'm trying to do it by neural nets, I use wavelet transforms rather than smoothing because it's much quicker and much easier. And then I just give the whole lot to a CNN, and off it goes, and it comes out with rubbish. That's TensorFlow's problem, not mine. So you build a scale space this way, and you'd like to see the same structure on all scales to be convinced that it exists. So, okay, you have to then cook. The recipe for cooking is rather interesting, or not interesting. You have to basically tell the machine how strong the feature is, and this depends on the eigenvalues, how convinced you are, in other words. You then have to define a signature so that can give you a map. And the signature, which is a combination of all this stuff, basically exists on each level of that you've created. And what happens is that you're then going to pick out, for a given point, the level upon which the signature is the strongest. And that point is a filament point. If its signature is a filament signature, it's a void point. So this is how you identify it, but you identify the single strongest point. Again, that can be improved. And again, with neural nets, that'll be a lot easier. It's persistence. You want to not only want to have the maximum, you want to have a nice persistent maximum. So you get this kind of stuff. I'm not going to explain what that is, but you start with your eigenvalues here on the left, you put them through a whole pile of filters, and then you get the answer out. And the answer looks like this. Now, the original field is shown at the bottom right, that's a density field. And the advantage of the nexus mechanism is that you can actually, you don't have to use density fields, you can use tidal shear fields and everything like this. So here is the filament structure found by, on simply the density, velocity divergence, the tidal field, the velocity shear, and then we can calculate all these. And Nexus Plus is the most interesting one because it takes the logarithm of the density, and that makes it almost Gaussian, and changes the dynamic range, and so you get lots of all the tiny little hairy stuff, which you might or might not believe, but you can actually see it. See a little filament there, a little filament there. So the power of Nexus is that we can take any parameter from a model or even data. I'll come to that. And the conclusions basically that you can draw are like this. This is from the P Millennium and Eagle surveys done at Durham by Marius Corton and Punya Ganeshire. And they show you basically what in these models that are the fractions of nodes, filaments, walls, and voids. And these are the fractions. And you can see that this is the number of particles. So voids actually have a fair number of particles in them. It's quite surprising. They're not empty. Right, mass functions, you can do everything you like. So there's a paper about it, telling you about the mass functions of the and the evolution of all how the masses of galaxies in the filaments are, and how the evolution of a galaxy of a given mass. If a halo has 10 to the 14 solar masses, it's like you're going to find it in a node, and you'll find filaments at 10 to the 12. You might find the odd node where filaments actually intersect. So you can do all this. I mean, it's a rich picking field. The interesting thing about this is that you can study the difference between these various cooking recipes. If you find this is the whole back. Here we have the whole Nexus Plus filaments. Yeah, this is Nexus Plus filaments, and this is the one done using the shear. And you can see there are substantial differences. And this is because the shear field actually has a bigger range of size, and so defines a lot rather larger and fatter filaments. So let's skip this. This is probably the most important result, which is the alignment of galaxy spins in filaments. And what you see is that they're not random. The random line, this is the inclination, rotation axis, and the filament itself. And you see an excess here at 90 degrees, and a deficit at 0 degrees. And it depends on mass. The high mass ones go that way, and the low mass ones go that way. So if you look at a sample, this is papers published on Archive. And so a problem which was totally unsolvable a few years ago, we now know that galaxies are aligned. Things which several PhD theses were written saying, can't find anything, and no result PhDs. Very sad. Really, I actually did some work looking at very early on, and yeah, I'm done. And we found it in a sample of galaxies which are really edge on, because when the galaxies are really edge on, you have no doubt where the spin axis is. It can't be projecting towards you. It has to be perpendicular to you, so you know the orientation. And we came up with this very low order statistic, and we see that basically we see what we expect to see because the sample is too small to discriminate between low mass and high mass galaxies. Anyway, I think that's about it. No, I won't go into topology because I think that'll happen in the next talk or so. Pictures? Pretty pictures? No. Okay, I think I'll stop there because my voice is dying. And thank you for your attention, and apologise for being drony at a low level of frequency. Thank you.